So, good afternoon. My name is Andri. I guess most of you know who I am. So I'm going to talk a little bit about a project that I guess most of you have heard about, and that is taking the H2S that is being emitted to the atmosphere from most geothermal power plants in the world and try to put it back into the ground where it originally came from. So in fancy words, it's called H2S sequestration. It basically means bringing the hydrogen sulfide back to the ground and mineralize it as sulfide minerals in the reservoir of geothermal systems. So basically this means that we are trying to make a geothermal power plant as a closed system, bring the fluid to the top, run the turbines, and then pump things back to the ground. So far, I guess most geothermal power plants today, they have this mostly in terms of they re-inject or inject back the wastewater into the ground, but then the vapor phase or the steam with its gases is usually emitted to the atmosphere. So sulfur is one of the key guys in there. It's found in both the vapor and the water phase. And today, together with steam, it is usually emitted to the atmosphere together with CO2 and hydrogen and many, many other things. So I guess maybe the key elements here that we are somehow unwanted into the atmosphere are CO2 as a greenhouse gas. Methane is of course also a greenhouse gas, but it's much less of an importance because of lower concentrations. And then it's hydrogen sulfide. It's basically just the smell. And this has been on the news here. People have been measuring this, monitoring this, associated with the Nesjavellir, in particular the Hellisheiði power plant up in the north. And there are clouds or plumes of gases that come over. And this is not good in terms of H2S because relatively low concentrations, atmospheric concentrations, can be bad for human health, as well as H2S can convert to sulfuric acid and cause all kinds of acid rain type damages for vegetation and so on. So basically, the whole idea here is to take this guy that is being here emitted to the atmosphere and take it back into the ground. So you can look at this some kind of a conceptual view here. So you will have the production wells taking the high temperature fluids up. Here's a production well into the power plant, and then you have the wastewater re-injected, and then the steam as well, or the dissolved gases into the wastewater. So it's some kind of making the geothermal power plant system as a closed loop. So just bring it up, run your turbines, put it back in. Everything that you don't want is going back to where it came from. So this is not a non-trivial thing. And the reason it's a non-trivial thing is that we have never done this before. Never in the world. We have tried to inject gases with any success at high concentrations for a considerable period of time. So there are many, many unanswered questions, both regarding the engineering, I won't talk about that, but both the engineering and then the hydrology of the system and the geochemistry. So my part of this project has to do with the geochemistry. Does this really cycle work? And this is just to give you an idea, and I think last time I came here, I also showed this diagram here, or this is basically the way we approach these things. We don't just approach it from one direction, we approach it in various ways. We do modeling, we try to simulate what is going on. We try to mimic this on a small scale in the lab. We develop some techniques how we can actually follow if whatever is going on is possibly going on, and then we scale it up to natural systems. So today what I'm going to talk about a little bit, or mostly, is that part here, and then how we can somehow possibly prove if this whole cycle in the ground is actually working. So this is what we are hoping to happen. Basically, we have basaltic rock in the reservoir. We inject the H2S, CO2 as well, with the wastewater and a little bit condensed steam. And we are hoping to mineralize this in the reservoir in terms of minerals like sulfides or other types of sulfur. And this will simply then stick in the reservoir as a permanent stable form. So the first approach to this problem to basically see is that reaction occurring under geothermal conditions was done in the lab. Okay? So this is a lab type geothermal system. So this would be your injection fluid. Okay? So this is a wastewater and H2S and so on. It's pumped at pressure into the reservoir, which is simply just a reactor, a small reactor. And then you can think of the sampling point as your production well or your reservoir composition and so on. The nice thing here is that you can vary in a relatively easy and short time different types of scenarios and basically look into your reservoir on a small scale. The results that we often obtain from tests like this, we put into verify our simulation codes that then we scale up to a big geothermal system. So this is basically a picture of a geothermal system in the lab. That's how it looks like. It's relatively simple. So this is a 1 liter bottle, so it gives you an idea of the size. I mean, this fits onto the table here. So it will be a solution of H2S and solution of some brine, pumped in, some sampling things. And this would be your high pressure, high temperature reactor. So a reactor like this, we run this from maybe 100 degrees up to 450 plus degrees up to a few hundred bars if you want, or just lower. This is always, or usually in a flow-through system like here, it's a single phase system, so we're looking at liquid only or vapor only or something like that. So these are the conditions that we have looked at so far. So H2S concentrations injected onto the column to a concentration that are similar to the tests that we have already started up at the power plant. And these are the temperatures, a little bit of the areas of the re-injection part of the Hellisheiði geothermal system. So it's maybe around 200 to 240 and maybe even lower because there are some thermal effects or cooling because of the low temperature of the re-injection fluids. So then basically what you can do, you can follow. Okay, and there's a dot line type diagram. I'll take you through this. So basically, this is what comes out of the reactor. This is after we have injected, basically injected in here, a known concentration. It reacts in your imaginary lab geothermal system, and this is what comes out here. And then the ratio, which is here, tells you how much H2S has actually been mineralized. So 1 means nothing has been mineralized. It just went through. 0 means that all your H2S has been mineralized. And as you can see, there are different temperatures, conditions, and so on. I mean, maybe the important part is that through the experimental geothermal systems, we are seeing mineralization of something like 30 to 70, 80%. So a fair enough fraction of our H2S is being mineralized. Okay? We are seeing the minerals. So this is just then opening the reactor and looking at actually the reservoir rocks, if you want to think about it that way. So we want to find the sulfides. And you can see that there are plenty of sulfides here. These are SEM pictures. There's also clays, the dissolution features. There's a lot of clays in some cases, lots of sulfides and so on. So we are really seeing the minerals that we see under the conditions here. The important thing then, in a plot like this, you see that the concentration that comes out, and this results in not a full mineralization of all H2S, is that there is always a background on equilibrium concentrations of H2S with mineral buffers in the systems. So you can think of there's a natural background that is not 0. So to see if you're actually just not getting the natural background, you can compare it within geothermal systems, and that's what you see here. So you can think of, this is the concentration of H2S as a function of temperature. This would be some kind of a background on equilibrium concentrations. This is actually the measured concentrations in the head-decided geothermal system as today. And these are then the concentrations that we are seeing at the outlet of the reactor. So basically what you can see is that at the low temperatures, we're completely out of balance, if you can think about it that way. But above 200 degrees, we are very close to basically the background concentrations, meaning that we mineralized the H2S to sulfides until we got close to the equilibrium background natural concentrations, and that is where we sit. What we are particularly also interested in how we see on pictures like this. I mean, I don't know if you see this so easily, but this is an experiment at 200 degrees that took 14 days, 18 days, and etc. So you're seeing mineralization not in terms of weeks, months, years. It's occurring almost instantaneously, okay? And so what is then controlling how fast this happens? That also falls out of things like this. So you can go back to your reaction like this. How fast does actually the rock dissolve in this mixture of H2S and water to form something like that? This is actually what we're seeing happening. And what we see is it's basically the rate of the dissolution of the basalt. How fast does the rock in the reservoir dissolve, forming iron, because you always need iron. So this is basically the release of iron from the basalt. These are the measured and theoretical values as a function of temperature of the release. And you can see that the formation of sulfides, pyrite, which is an iron sulfate, is proportional to the release of iron from the primary rock. So basically what this means is that the quantity of this forming is not controlled by how much of this you put in, but how fast this actually dissolves, okay? And in terms of the real system, at least if we have glassy rocks or basalts like we are having in a lot of Icelandic geothermal system, this is dissolving relatively rapidly at these geothermal conditions. So these conclusions, together with modeling conclusions and solving major engineering difficulties, resulted in that this is now being done on a full scale. Not all the H2S from the head-decided power plant. At the moment, it's 10%. But it's been running since October, and this is the second try, and so far it looks very promising. If it continues to do the same thing for a long time, that's something that we need to see. But this is all good. We're seeing in this lab, we are doing the modeling, but how can we actually demonstrate that the H2S that we re-injected into the reservoir actually reacted with the reservoir rocks forming sulfides? Okay, we see it in the lab, we see it in our model, but we don't necessarily see it in the reservoir. But this is what we think it's forming, we're pretty sure it's forming, but how can we absolutely be 100% it's forming? And the key to that, and this is what we are starting to try, are sulfur isotopes. Okay? So sulfur isotopes, they can be used to trace reactions, what reactions are going and what direction the reactions are going. So sulfur, this is basically, sulfur is an obvious choice because we are injecting sulfur. So sulfur has several isotopes. Thereof, there are 4 isotopes that we can today measure, okay? It's a non-trivial thing. There are actually 2 labs in the world that can do that. But we can measure 32, 33, 34, and 36. the way we do that in practice for isotopes usually is we don't measure the absolute concentration of a given mass. We measure a fraction between two masses. So classically what we do, the 32 is the way the most abundant, and then we measure the ratio of 33 to 32, 34 to 32, 36 to 32, and then it's given somehow like the ratio in your sample relative to a standard times 1,000, and then you can also link the different isotopes through mass-dependent isotope laws. So we have worked a lot on this because this has never been done before. We have no idea how to do this, okay? We know how to measure it. We don't know how to sample this. We don't know how to prepare the samples, and we don't know what the numbers mean. So this is one of the things that we have been working on over the last 2 years, how to collect samples of geothermal fluids at surface for production wells and extract the sulfur in order to do the sulfur isotope analysis. So this is basically a twist of a normal type of fluid sampling, different reagents put into the reagent bottles, some extractions in the lab. This is actually a lot of work because it's almost like a slavery. It takes forever to do that. And then the mass analysis is a relatively straightforward thing to do. So just to give you an idea is that taking a sample like this takes maybe a couple of hours. Extracting one sample takes a full day, and then you do maybe 8 samples a day here. But we can use this to follow possibly if we are mineralizing the H2S, or if it's just mixing, flowing through, oxidizing to sulfate or something else. So sorry about that. This is maybe a little bit complicated thing, but it's basically telling us that the way things evolve as a function, you can think of this as a degree of mineralization. Okay, that's what's on the x-axis. And this is what is happening to the different isotopes. Okay, this is theoretical, but basically what happens is that the pyrite is isotopically heavier compared to the sulfide in the water, and eventually if you have pyrite formation, your sulfide in the water after pyrite formation becomes progressively lighter with more pyrite. So basically if you inject something like this here that has a 0 and you form a lot of pyrite, your evolved water, your sulfide in your mineralized water will have quite negative values. Okay? So this is some kind of a summary of that. This is the conditions in the reservoir today. Okay? This is what we are injecting. It's actually a little bit different. If we have pyrite formation, the production fluid will move towards here. Okay? If it's just diluting and mixing with the reservoir and nothing is happening, there's no pyrite forming, it'll sit somewhere on a mixing line like here. If the sulfide is being oxidized, like we are really worried about, if it oxidizes to sulfuric acid, it means that eventually we may have an acid sulfide reservoir, which is not good, then the isotopes will move somewhere into here. Okay? So we haven't started this. This is going to be the second tracer test of the Sulfix 2 project, starting hopefully sometimes in the fall, and seeing that we are injecting this, and if the production fluids in the close-by wells of the injection well don't slowly move towards here, meaning that we're actually mineralizing our sulfide as pyrite. The pyrite that is left in the reservoir will be isotopically heavier, both in terms of 33 and 34. So at the moment, the steam from the Hellisheiði, the 10% of the H2S emitted from the Hellisheiði power plant is now being re-injected. It's going well so far. It's the second attempt. Engineering, it looks promising. Geochemically, it looks promising. There have been tracer tests that have been done, and there's a very thorough monitoring program, and it is actually looking very nice, but at the same time we have to keep in mind it's only few months that, or few weeks that this has been done. If this continues nicely for the next months, the quantity of injection will increase, and then the sulfur isotope monitoring program will be implemented in order to demonstrate if this is actually truly working or not. I haven't done a lot of this work. I'm just running the bookkeeping system here. But the people really behind this, Suhei Ono, a prof at MIT, he was very generous, so we have a full access to his multiple sulfur lab, which is very nice because it's one of the 2 labs that can do this in the world. Hanna is doing a lot of the sulfur chemistry. Jói did his master's on this sulfur isotope chemistry. Snorri is really the brain behind all these experiments that I showed. And then Nick is doing a lot of the sulfur isotopes preparation that takes forever. Okay, so thank you very much.